Okay, so today we'll take a look at multivariate distributions, okay? Okay, and so, we can start off with kind of the Metropolis Hastings algorithm for the multivariate case of the Metropolis Hastings algorithm, okay? So, and it's exactly the same, okay? Multivariate Metropolis and Metropolis Hastings algorithms. Okay. So I'll say the algorithm is the same. All right, so now your PDF is going to be some, what have we been calling the target distribution? It doesn't matter, right? F, okay. F, and now it's of some multivariate vector, x, okay? So your PDF is this. And then basically you propose x star using G of basically x star given your current value of x. Okay, so you've got some proposal distribution. Okay, but this time it proposes a multivariate x. Okay, and then P move will be the min of 1 f of the proposed divided by f of the current. Okay, and this is Metropolis, or the min of 1 and the proposed divided by the current times basically whatever else it was for the Metropolis Hastings thing. So if it's not a symmetric thing, then okay. So this is exactly the same thing. All I've done is taken my x's and put little vectors on top of them, or like the little arrows on top, or if it was printed, we would make them bold-faced to say that they're multivariate, but it's the same, right? Oh, sorry. And then we accept the proposed value with probability P move, and then and if accepted, x at time t plus 1 is going to be the x star, and if rejected, you just reuse the current value, right? X at time t plus 1 is equal to x at time t. Okay, so it's exactly the same. The only thing that we really have to change is how do we propose multivariate values, right? So so like if you have a multivariate thing in R, like the multivariate normal, you would just use R, NVT norm, and things like that. Oh, okay. Let me, before we get into that, I wanted to talk about something from the homework that's due today. And this is just a point of clarification, or I don't know, explanation. maybe I'm giving away some answers here. That's fine. Let's see. It's homework 4. Let me. Okay, so these it might be some of the plots that you might see for the different levels of sigma that you've chosen. Okay, so the target PDF should look kind of like this. Should look kind of like the sine function, but raised up and things like that, right? And so you have, so you figured out like how to do your function, okay? And the target distribution looks like this, okay? And I'd say all 3 like kind of gets it, okay? But well, maybe not the first one. All right, and then when you look at the chain itself, what are we seeing? Okay, we see something that looks like this. This almost looks like a cityscape. All right, like the New York skyline or something. And then this is, you know, a lot more jagged. And then this is all over the place. Okay. And of course, your things will look different from mine. So what's going on? Well, the thing here with this first one, with the tiny sigma in the proposal distribution, basically it's only proposing, like if you're currently at 1, it's going to propose like 1.1 or 0.9 or things like that, okay? And so pretty much almost every value it proposes, it's going to accept, all right? And you might think like, oh, don't we want that? Don't we want to like accept every single value? And the answer is no, we don't, because you can end up like wandering too much in one zone, right? So you would kind of have like these 2 peaks and stuff, and it's possible for you to kind of end up over on this side, and just because you're accepting almost every single value, you just kind of wander around there for a very long time, and you kind of oversample a certain region, okay? On the other hand, we have sigma equal to 20, right? So you're currently at like the value 2, and you propose a value like 18, or you propose a value like -7, okay? And so what ends up happening is, you know, so here like we're at 2, and we're proposing all sorts of terrible values, and like the first, it looks like 30 or 40 proposals all got rejected, okay? And only when we proposed, it looks like 7.5 or something, did we say, okay, this one is within reason and we will accept it, okay? And then we were at 7 and we proposed a whole bunch of things and we just kept rejecting them. So we kept reusing 7.5, 7, whatever it was, over and over and over again until we got a new value. And so we're getting this thing where, you know, we propose a value and most of these things get rejected, and when we do accept a value, we're kind of stuck there for a while because everything that keeps coming by, every value that gets proposed is terrible, okay? And so I guess you can think of it as like someone, as far as like, I don't know. Okay, maybe this is a terrible example, but like maybe you know a few people in your life. Okay, one who has like no standards as far as who they enter a relationship with, right? And so every single person that comes by, they're like, all right, we started going out or whatever, and then and you're just like, this is a terrible person. You should not be accepting these values, type of thing, right? So everything is that, right? And then the other is maybe this is not a good example because it's actually what's being proposed are terrible, right? So well, okay, so maybe that's bad. But basically, we're rejecting over here. We're rejecting everything because everything that's being proposed is not a good option, right? we want something in between where we get enough movement through the distribution space, okay? So that we're over at 2, but we can kind of propose over here at 5 and over here. And yes, sometimes we'll propose some bad values, like over here at 10, or sometimes negative values and things like that, but we'll reject them, okay? And sometimes we're up here and we propose something like down here and we say, yeah, I don't want that, okay? And so kind of the ideal situation is you want an acceptance rate right around 50%, maybe a little bit higher, a little bit lower. I forget what somebody did some analysis as far as what's going to give you kind of the best situation. But you don't want to accept everything, and you don't want to be rejecting everything either. You don't kind of want a balance there, okay? And so that's what we're supposed to be seeing. This here is just kind of the random values that actually do make it into your sample, and so it looks quite jagged, okay? All right, okay, so anyway, going back here, multivariate distributions. The Metropolis algorithm is exactly the same. Metropolis Hastings algorithm is the same. And so as far as proposal distributions, you have a few options, right? So I'll just do for the Metropolis algorithm. And we'll do the multivariate case. Okay. So what do we have for the univariate case as far as proposal distributions for the Metropolis algorithm? So for univariate, we said if we are at xt, okay, then we can propose from what? Okay, so we can propose uniform. And where would what are the bounds for a uniform? Yeah, I mean plus minus some arbitrary value, but sure, 1 sounds reasonable, okay. Oops, xt minus 1, you know, just some arbitrary thing, right? Okay, so if we have that for the univariate, the multivariate is going to be the same, all right? So let's just do the 2D case. So basically, here's x at time t, and we would go plus 1, minus 1, okay? So the 2D case, okay, we are at xt, okay, which is some two-dimensional point, and we can basically propose, so this will, I will say this will be x1 at time t and x2 at time t, okay? So we can propose a new point, x star, from basically where x1 star comes from uniform x1t minus 1 and x1t plus 1, and x2 star comes from uniform x2t minus 1 and x2t plus 1. Okay, so so basically it looks like this. You have this point is x at time t, and then here is, this is x1 minus 1 and x2 minus 1, and then this is x1 plus 1 and x2 minus 1, etc., right? x2 at time t. And you can propose kind of within, anywhere from within this span. Okay? So that would be okay. Or you can also do, if the univariate, the other one was kind of the Gaussian. Okay, we said if we are at xt, you know, then we can say x star comes from the normal distribution centered at x at time t with standard deviation equal to 1 or something like that, okay? And so for the multivariate case, so we'll say if we are at xt, then x star will come from the multivariate where the mean is x at time t, and sigma can be, actually I have to write, the sigma matrix can be something like this. Okay, and so, so the univariate, you're currently at xt, and you're going to propose values near xt, and then the multivariate, you're at xt, and I guess it's the Gaussian thing, right? So it's I don't know how to draw this thing. It's the, I think you know what I'm trying to draw, okay? It's hard to draw. Something like that, all right? Does that kind of make sense? All right, and then you just need the functional form, or at least something proportional to the functional form of your PDF, target PDF, to get your p-move. Okay, is that good? Any questions on this? I think homework 5 or something, you'll do something like this, right? You'll propose from some kind of multivariate thing, and then you'll accept or reject or things like that. Okay, there's an issue, all right? So for the 2D case, this seems to work fine, right? But we can also, we end up with the curse of dimensionality. And basically, just as we climb and get more and more and more as we get into higher dimensions, it gets really hard to propose a good value. Okay, curse of dimensionality. It gets increasingly difficult to propose a good value as we increase the number of dimensions. Okay, so all right, so let's say, okay, so in the univariate case, let's say we have some kind of, this curve is the target PDF. Okay. And let's say we are currently here. Our current value of x. Okay, this is our current value. Okay, and let's say our proposal is just, we're going to use the uniform proposal. So, you know, we're going to propose basically from here to here, okay? And what will happen is basically, if we propose, we're like guaranteed anything over here will get accepted, okay? Will be accepted, and then and the stuff on this side might be rejected, right? Maybe it's accepted, but it might be rejected, okay? But basically, we have at least 50% acceptance rate, right? So at least 50% will be accepted. Okay. I got to go on to the next slide here. All right, is that all right? So, you know, we're kind of starting off in this not so great location, but we can say at least 50% will be accepted. We're in agreement there? Okay, what about the bivariate case? Okay, so let's say our target PDF looks like this. Okay, so this is like the peak. All right, is that all right for the target PDF? It's some bivariate thing, okay? And let's say our starting location is right here. Starting location. So this is a junky starting location, right? And we want to eventually move towards the middle. All right, as far as my proposal, let's say I use the uniform proposal again, okay? So uniform proposal, so x1 star will come from uniform of x1t minus 1 to x1t plus 1, and same with x2 star from x2t minus 1 to x2t plus 1, okay? All right, so my proposal distribution will look like this, all right? Okay, what proportion of my proposal distribution will be kind of guaranteed acceptance? Okay. So I can kind of divide this into like 4 quadrants, all right? And anything over here, this will get accepted with 100%, okay? And then probably, and then everything else, this will probably be rejected, and then, you know, everything else is kind of something in between, okay? So probably something, okay? So as the number of dimensions increase, the area where I'm going to accept, I'm kind of guaranteed acceptance will shrink, okay? So with 2 dimensions, my kind of guaranteed acceptance goes down to 25%, okay? And in 3 dimensions, okay, you know, now you are proposing in some kind of cube, okay? Oh, geez, this is nightmare. Okay, so you know you're centered right here in the middle of the cube. Okay, and now you have kind of these 8 boxes around, and only 1/8 will be kind of closer to the center, and a lot of other stuff will be farther and farther away, right? So kind of the only 1/8 is guaranteed to be kind of closer to the region of high probability. Okay, and as the number of dimensions increase, it gets harder to propose a quote good value. Okay. So if you have something in like 20 dimensions, okay, it's gonna, and let's say in each of the dimensions, like you're using like this uniform thing, okay, uniform proposals, and this would not be a good idea for this exact reason, but if you have a vector in 20 dimensions, okay, and we will say, you know, so we have x as a vector in 20 dimensions, okay, and then we'll say for each x1, x2, all the way up to x20, we'll say half of proposed values are good. Okay. And we can see that it's going to be, if we're just going purely randomly, it's going to be hard to make sure that all 20 random values end up on the good side. Okay? Because you might get like, it really only takes one proposed value to, one of these 20 values to, proposed values to be bad for you to kind of like reject the whole proposed value, okay? So if we're just kind of, it's kind of like using some kind of random machine to suggest an idea or something. I'm trying to think what would be comparable. I don't know. Okay, I don't. Do you ever play like video games and there's like a character creation screen? Okay, and on the character creation screen, you might have like a choice of picking your character's hair color, your character's like, I don't know, eye color and facial features and this and that. Okay, and maybe for all of these things, you like half of the options, right? You like half of these hair color options, you like half of these face options, you like half of these whatever eye color options and stuff like that, okay? Sometimes you might have like just a random button, okay? You hit randomize and it's gonna just randomly select from all of these things. It's gonna be, if you just keep clicking that randomize button, and if there's like 20 features, it's going to be hard for the computer to just randomly select 20 features where all of them are features that you like, okay? And chances are you might like some of these things that it's randomly selected, but some of them you won't like, right? And if the only tool we have for generation is just random selection, and we don't get to just say like, okay, let's keep these and just change these ones that I don't like, you're gonna be clicking that randomize button for a long time. You're gonna be proposing a whole lot of values, 20-dimensional values, And very few of them will have all kind of 20 things that are acceptable as far as the PDF, kind of the P move being high enough to be accepted. Okay? So we'll say half of the proposed values are good, and there's a low probability that that we can generate generating a full set of 20 that we like. Full set of 20 values that we quote like. And we'll accept. Okay? By like, I mean P move is high enough to be accepted. So that's the problem of just using kind of the Metropolis algorithm in something that's really high dimensional. All right? And so what we're going to do is we're going to use something called the Gibbs sampler. Okay? And so the Gibbs sampler says we're going to break apart a high dimensional PDF into a whole bunch of univariate PDFs. Okay? And breaking it apart, however, though, is complicated because chances are that there's kind of covariance and interrelational things, and so you're going to break it up into a bunch of univariate PDFs that are conditional on all of the other values. Okay. I mean, okay, so let me just kind of pause here. The Metropolis algorithm, according to all of the theory, even if you're doing it in super high dimensions, in the long run, it will work, okay? It's just, we might not have enough time, right? It might take days or hours if you're using the Metropolis algorithm where you're rejecting like 95% of proposed values, okay? And so in the long run, if you let it run long enough, it will work. It's just, it might not be something that we like. Okay. All right, so the solution is going to be known as the Gibbs sampler, okay? And what we do is we break up a multivariate PDF into several, or I'll say it, into a bunch of univariate conditional PDFs. All right. So if we have f of x, which is the f of, say, the values, I guess this would be the joint distribution of x1, x2, x3, x4, etc. to xd, okay? We're going to break this up into f of x1 given x2, or I guess we can do it this way. Okay, it'll be f of x1 times f of x2 given x1 times f of x3 given x2 in x1 times f of x4 given x3, x2, x1, etc., etc., etc. Right? So that would be kind of the total joint probability. And that's fine. what it ends up looking like is, let's just do kind of like a bivariate case. Okay, so let me do like a bivariate example. So we have f of x1 and x2. And so the traditional regular Metropolis algorithm will say, we propose the coordinate x1 star and x2 star coming from g of x1 and x2 given kind of our x1t and our x2t. Okay, so that's the regular Metropolis algorithm. The Gibbs sampler says we're going to propose x1 star from basically f of x1 given x2, all right, at time t. So we use the current value. So basically we quote lock in current value of x2 at time t. Okay, and we get this. Actually, not even. I'm going to just draw x1, and this will be at time t plus 1. And then x2 at time t plus 1 will come from f of x2 given the value that we just drew. Okay, so then we lock in the value of x1 that we just drew. Okay, so we draw a value from this. So it requires that we have to figure out kind of the conditional PDFs, and we generate that. And then once we get a new value here, we're going to generate a new value over here. And then we iterate. Okay. And repeat. Okay. So can I graph this? And do 3D R 3D plot of multivariate guessing. How do I do this? MVT norm plot. Can I do this? Maybe I can just copy. This is what I want. Okay. Multivariate. That's all right. I don't need to actually draw it myself. I'll just look for something. Can I do this one? Let's take this one. Okay, so this is what this is what we want. See, so let's say this is our target. Okay, so this is our target PDF in 2 dimensions. Okay, and basically, let's say at t equals 1, let's say x1 is, we'll say, I'm sorry, x2, or I guess y. Let's say y is, I don't know, 20, okay? What we do is we kind of lock in this value 20, and I don't know if this is actually the thing, but I'm just tracing. This is really hard to do, okay? So I'm gonna just trace the contour here. Okay, so at time, at time t equals 1, y is 20, all right? And basically this red line represents, this is f of x1 given, or this is f of x if we lock in y equal to 20. Okay, so this is this thing, which is itself a normal curve, but this is the value that we have when x, this is the distribution of x when y is equal to 20. Okay, and so from here, so maybe this is equal to the same thing as the normal distribution centered at, say, 50 with standard deviation equal to 12 or something, right? Okay, and then so we will generate at time t equals 1, y equals 20, and we generate x coming from this thing, f of x given y is equal to 20, okay, which is the same thing as basically doing our norm 1 value, where the mean is 50 and the standard deviation is 12. I just made up these numbers, okay? All right, and then so maybe if we do this, we get x is equal to 65 or something like that, right? So that's one possible value, okay? So so this is going to be our value of x at the next iteration. Okay, so I'm going to use, I guess, purple. And so now I'm at x is 65, okay, and I'm going to trace what this thing looks like, okay? Okay, so we're like going to slice the thing here, okay? And so so maybe I so then at t equals 2, x will be 65, and then we generate y coming from f of y, where we've locked in x equal to 65, okay? And so maybe this is, you know, I don't know what this is. This is equivalent to doing our norm of 1, and I don't know what the mean of this thing is, maybe 35, and standard deviation 15 or something. Okay, I'm just making that up again. All right, so we have something here, and then we're going to just generate a new value. And then so let's say y is equal to 31 or something like that. Okay. Okay. And then you'll repeat, but this time y is locked in at 31, and you're going to have a different kind of slice here. So for every value, you're going to kind of just take the slice of the multivariate, and when you take a slice, you're going to get basically a univariate function, and you use the univariate function to generate one value. And then once you take that thing, you're going to slice in the other direction and generate one value from the univariate thing. Okay, and so the thing is there's no p move to calculate, because here we're just generating directly from this basically the sample the target PDF itself. It's just that we've made them univariate. So we're basically breaking up the entire multivariate PDF into a whole bunch of univariate ones. Okay. We'll take a closer look at this on Monday here, but this is how we're going to start dealing with high dimensional distributions.